Hi, I'm Fernando Pereira from the Federal University of Minas Gerais in Brazil, and today we continue to see how we can use machine learning techniques to predict properties of programs. In the last video, we saw a bit what is predictive compilation. This time, we will take a deeper look into a particular machine learning technique, linear regression, and how we can use it to predict the speedups of optimizations. So we shall use linear regression to carry out predictive compilation. And the goal of the model that we will build will be to estimate the amount of code size reduction that we can get with some sequence of optimizations. I will be reusing, in this case, material from this paper, exploring the space of optimization sequence for code size reduction insights and tools. We want to extract characteristics from programs and associate these characteristics somehow with sequences of optimizations. These program characteristics are essentially numeric vectors that describe the program. So let's consider that we have two programs. These are different programs. We can represent these programs as vectors. Notice that these vectors can have multiple dimensions. They can be 2D matrices, for instance. The meaning of these vectors, just for now, is immaterial. We will talk about meaning later on. But anyways, the vectors can be also, unidimensional arrays, or they can simply be scalar numbers. But the most important question which we must answer is how to transform a program in numbers. I mean, we have programs and we want to represent these programs as numeric vectors. This transformation should be fast, polynomial time. We don't want to spend forever to transform a program into a set of numbers. It must be also deterministic. A given program will always produce the same numeric representation. It's okay to have collisions. It's acceptable that two different programs produce the same numeric representation. There are more programs than numeric vectors, in other words. Notice that this implies that the transformation is one way. From a program, we always get a numeric vector, but from a numeric vector, we might not get, the original program back. There are many different techniques to transform a program into a vector. Any function that performs such transformation is called an embedding function. There is a nice paper from 2020 written by Brockman, Ortol, and Castrillon that discuss a number of different embedding functions. If you want to know more about them, I recommend you read the paper. We, for simplicity, will use one of the simplest embedding functions ever to explain how machine learning works in this domain of compilers. This very simple embedding function is the histogram of instructions in a program. The idea of the histogram is very simple. Count the number of instructions. Each position of our numeric vector corresponds to a certain quantity of instructions. For instance, if I have this program here, let's take a look into its instructions in LLVM format. These are the instructions that constitute the CFG of the program. Here's the vector of instructions. This vector has 65 positions. Currently, in LLVM, we count 64 different opcodes, but the first position 0 does not correspond to any instruction. The third position corresponds to the branches, for instance. And you can see that we have 6 branches in the CFG. The complete list of opcodes available in the instruction.def file in LLVM. And now, how can we use the histogram to predict the best sequence of optimizations for a program? Or, equivalently, let's focus on the regression problem. We want to predict the impact of a given sequence of optimizations on a program. In this problem, our input is the histogram of instructions of the program plus a sequence of optimizations. And the goal is to predict the final number of instructions produced by that sequence. Notice that usually we don't need to worry about all the instructions in a program. Lots of them are zeros anyway. We can work with a reduced set of instructions. For instance, here, let's focus on a subset of 9 instructions. Don't worry on why I chose these instructions. The answer is mostly because they tend to be common in most programs. Essentially, we are selecting some features from a larger set of program features. This is called feature engineering. So our embedding will be a vector with 9 dimensions. And we will try to write the number of instructions produced by the sequence of optimizations as a function of this vector. Don't worry, that's not as scary as it looks like. We want to build a function that approximates the number nsec, which is the number of instructions in the optimized program compiled with the sequence of optimizations called sec. And this number is a linear function of the number of occurrences of the different instructions in the program. This is our linear model. And so, our goal is to find the stand constants that approximate nsec for most of the programs. This process is called a linear regression, and it's one of the simplest kinds of machine learning models. So now we have to find out the stand constants, CBR, C-switch, and so forth, that approximate the actual behavior of the sequence of optimizations on programs. How can we find these constants? We do it via training. To train a linear model, we need lots of data. Data in this case are programs, lots of them. From each program, we extract the histogram of instructions. We extract the number of occurrences of the 9 instructions that we are considering. To get these instructions, we can use an LLVM pass, provided that we are counting LLVM instructions. It's a good thing to first preprocess the program with an optimization like man-to-reg, which moves values from memory into virtual registers. Anyway, here's an example of code that you can use to count opcodes. If you want, you can come back to this part of the class later on and see how this pass works. Once we have lots of data, we can train a linear model. I'm going to show how to do it using the R programming language to this end. You can use anything, of course. Most people work on Python. I'll be using R just because it's so easy to train a linear model in this programming language. I left some data that you can use to train a model in this CSV file. You can grab it online using this URL. This file contains data for 203 C programs that we got from Engebench. Once you get the file, you can easily read the data using this R command. It might be a good idea to shuffle the data. You can do it using the sample function, which is readily available in the R standard library. Let's split the data into a training set and a test set. We will separate 80% of the data to form the training set. And then we can get a linear model. For that, we use the LM function, which is also available in the R standard library. The goal of this linear model is to predict OS, the number of instructions of the program when it's compiled with clang -OS. And we shall build OS as a function of these 9 variables, which are the numbers of different kinds of instructions in the LVMIR for each program. Notice that these variables are all essentially the names of columns in our CSV file. Take some time to see that's the function that we had written before in the beginning of this class. Once we have a model, we can build a test set and use that to use the predict function from the R standard library to see how well we are doing. So in this case, results is a vector with the predictions performed for test, which is a set of data that we got in that CSV file that we read in the beginning. Let's plot the results of our prediction. So the y-axis are the results of the prediction, whereas the x-axis is the actual value that we observed in the test set. As you can see, most of our predictions are on the diagonal, or very close, so we got a good model, I'd say. Let's take a more detailed look into this linear model. Again, that's important. You need to convince yourself that you've just written in R the equations that you had written before to describe our linear model. We can even see the coefficients using the summary function. So here they are, the coefficients. For instance, the coefficient of the branch dimension of our model is 1.0078, and the intercept, the constant that's not the coefficient of any variable, is minus 0.8488. So basically, what our model does is to solve this equation for each program. See how the coefficients in the summary function match up in the original equation that we had. Do you remember that program that we had seen as an example in the beginning of this class? Here it is. That's the histogram of that program. Let's try to predict the number of instructions in the optimized program. We can build a data frame with exactly the instructions that we consider in the model. And for that program, we predict that it will have about 13 instructions once optimized with Clang-OS. We can get this result directly by multiplying the coefficients of our linear model, which you can see in this vector coefs, by the vector that represents the histogram of the program. And that's what we get. That's not very different from the result in the model if you do it explicitly using like this cross multiplication. And how would you check the number of instructions in the actual program once you optimize the program with Clang-OS? Well, we can compile the program using Clang-OS, and then we use OPT to count the number of instructions. In this case, we get 16 instructions. What's not too far from the 13 that we had predicted. And that's very different than what we would get had we optimized the program with -0, for instance. In this case, we would have gotten 37 instructions and not 16. And with that, I close this class on linear regression in compilers. There are many other examples of use of linear models in this domain. For instance, if you want to see how linear models can be used to predict silent stores, take a look into this paper. If you remember, a silent store is a store that deposits in memory a value that was already there. Or if you want to see how to use linear regression to find the best hardware configuration to run a program, you can find more about it in this paper. Anyway, we shall talk a bit more about other machine learning techniques in the context of compilers in the next class. Till there, you feel free to write me with questions or comments.